Start by stating the theorem that I stated last time, and it's what I want to prove, or at least explain how you prove it. So this theorem is that was a bootstrap multiscale analysis. So I start with a regular Anderson model, and by regular means that the probability distribution is Holder continuous. So, and I'm working in the dimensions. I'll be a bit more specific than I put yesterday. Turns out I can actually tell you this is not the best possible, but this is work. Suppose P0 is a number which is smaller than 1 over square root of 2,000 to the power d. This is not optimal in any sense, okay? Just an a gross upper bound, but it shows it's not an extremely small number. It's not infinitesimally small. It's a number. So there exists a number, and now let also theta, and this is a correction. The slide yesterday was missing this factor. Alpha mu for me was the coefficient of Holder continuity of the measure. Number between 0 could be up to 1. So I didn't put this here. So I need theta to satisfy. Then I want to put that there exists a scale L, which is going to depend on the parameters, such that if for some energy E and some scale L0 that is big enough, we have that the probability that for all x in Rd, the probability that the box is suitable is at least 1 minus this number. Then for every zeta between 0 and 1, I can find some minimum scale L of zeta, some small number delta, and some other positive number. And unfortunately, as you would hope, such that the following holds. So these are such that for every scale that are bigger than that, we have the conclusions of the multiscale analysis. One is that the infimum, since I'm doing it for all x, that the probability that an arbitrary box of size L of x is now regular, not anymore suitable. That's why we call it a bootstrap, is bigger and equals than a sub-exponential factor. And this holds for every zeta. We can achieve that. And second, if I take now this interval and I take x and y in Rd, since I'm taking boxes in Vd but centered points in Rd, and I want the respective boxes to be disjoint, the probability that for every energy in this interval, either this box or the other one is m zeta e prime. The prime was missing yesterday also. Regular. This is also 1 minus a sub-exponential. So that is a multiscale analysis. And from that we are going to derive all the results on localization. We already discussed that we can, and let me just remind to you that suitable meant that if I look at the Green's function, it decays polynomially in the length of the box. I need the points to be far apart all over 100, and regular is a usual exponential decay. This means that, but I will else actually define that it decays exponentially in the distance as long as x minus y is also bigger than equal to all over 100. So we start with polynomial decay with, if I can show it, and I know what P0 is in the continuum case there is a bit more dependence on the energies and other things, but not in the lattice. Then we can go from polynomial decay to the exponential decay and get either the single energy or the energy interval multiscale analysis, from where we are going to get localization. So let's then start.
Excuse me, could you please put those two blackboards a bit apart?
Okay, I'll have to, fortunately I realize I'll have to erase this soon. Okay. So what are the tools? What are the basic ingredients for the multiscale analysis? Well, the first one was the Wagner estimate, which we already discussed. And I have a regular measure, and remember that it simply meant the way we're going to use it now is going to be like this. The probability that this is big is bounded by some Q mu is essentially times the volume, and Q mu is essentially the concentration function up to a constant. The constant is not going to be important, so our hypotheses are, and I will state them now for Q mu, that's a Holder continuous. There is some constant. I did that for the concentration function. Let me use the same constant, or put a prime if you want, times T to the alpha mu, where alpha mu is a number between 0 and 1. So that's a hypothesis. That's something I know. This is a hypothesis. This is something we discussed last time. The other ingredient is what you get from the resolvent identity. And here, let me take a box of size little l, which are contained in a box of size big L. Could also be a situation when it is at the boundary. I don't care. Then, of course, we can write H, and omega is always being fixed. These are all deterministic. I can write it as the one in the little box plus the 1 on the complement of the little box in the big box plus what is left, which is an operator that lives in the boundary of the small box in the big box. So this is actually minus 1 for all of those bones and 0 everywhere else. From this, as usual, if I take Z naught in the spectrum of the operators, let me forget the indices. Let me call this H tilde. This is H tilde minus Z inverse. And I never remember if it is a plus or minus sign, depending the way you write it, of course. Here I think is a, where did I put it? Okay, I think I have a plus sign. If it's not, it doesn't make any difference, since you're going to take absolute value times the difference. This is a usual resolvent identity. Okay, and once you have that, and I can apply it, I can take the matrix element. So for the first one I use G, the matrix elements between X and Y. This is equals to the matrix element, let me put a tilde. For the second one, let me for that also. Plus, and here I have the matrix element of these elements, so I should have first between all possibles U and V, that should have G tilde XU. I should have the gamma of U and V, and I should have G of V and Y. But this is 0 unless these things are in the boundary of this box with respect to the other box, in which case this is actually minus 1. Yeah, I think actually I did the wrong sign. Not that it matters, but I think it's a minus here, sorry. I don't think it, if not, just correct it. This is minus 1, so I get this. And I'm interested in the case where I take X here and Y here, but in this case notice that for this operator it doesn't couple lambda little l to the outside. So the first term is 0, it doesn't appear, and the second term, well, by the way I wrote here, it could actually be also VU is up here, but not now. U has to be inside. Since I am inside and this decouple, I get the small one, X to U, times, and this is the one from the bigger box from V to Y. This is like the Simon-Lib inequality in statistical mechanics. Okay, and the way we actually use that, they'll do it. is that we have this, and you have a box inside, a point here and a point outside, x and y. This quantity here only uses information that's inside this box. Okay? It doesn't know anything about the outside, and the way we are going to use is simply that we are going to take the absolute value, and then, well, I'll take the maximum of this quantity. So the maximum of this quantity, let me use a notation. So this is a maximum from x to the of the absolute value to the boundary of this box. I get the absolute value at some point where it takes a maximum. And here I should have how many points I have here, which is estimated by a constant times L to the d minus 1, because this is a boundary. And so this is true for some V1, and V1 is in the exterior, oh, I think I used a plus, of the boundary of the little box in the big box. I don't know where V1 is. All I know is that V1 is somewhere here, somewhere in the outside boundary. And if I have information about, this doesn't move, that quantity here, so for example, if I know that I have a suitable box, I know that this is less or equals than 1 over L to the theta, and I can use this information and proceed. I have a small factor, and all I do, I have a similar term, but I move to here. So I'll have to show how to use it. Maybe I should write the correct definition. Okay, good. Now, let me introduce something else which is going to be useful to basically make the proofs efficient. And that was the reason I consider boxes that were actually centered in RD, not in ZD, to make this easier. And that what was the third tool, which I'll call suitable covers or coverings. So again, this will be a definition. Okay, and here I'll have to make another definition. I define this to be all points of y in ZD, y minus x less than equals than L over 2. I may also be interested in boxes in RD. That will just mean I'll put an R here. You see why in a moment. So my definition then would be that I take little l to be smaller than this. I take this box to be a box of this type, and I'll call the suitable covering, or L covering, or A suitable. Oh, actually, let me call it to change L covering of lambda L of x is a collection of boxes of size L So this is a box of size little l, where A is going to run what I'll call script L, And what are those? And those are just all points of the form, and I have to define what alpha is here, 2 alpha L of ZD. Intersection, and here I'm doing the intersection actually in RD. That's why I need the box in RD. And I have to tell you what alpha is. Where alpha is, I take the interval 3/5 over 4/5, and I take the intersection of the set. I'll explain where these things come from. Where k is an integer, and I could call a suitable covering, that would be fine. To simplify things, I'll pick up one. It doesn't matter which I pick, so I'll take the maximum of those. It's a finite number of the inter. I could have taken the minimum, it doesn't matter. Why is this good? This is good because of the following properties. This is good because we have the following lemma. So the lemma I'm not going to repeat. So I have the L covering of this box. One, the whole box is actually given the union of those boxes. Of course, it's not disjoint. So it is a covering. And the way we choose alpha, one of the things that we achieve is that if I have my box of size L, I start with a box centered at the center of size little l, then I add boxes like this. But these numbers are calculated such that it fits exactly here and the same to the other side, right? And up and down. So they fit that way. And that's where these come from. And that is actually the key property for us, that for every point in the box, I can find some element in the covering. So this is a box. I'm putting an upper script. This is not the center, such that there are two ways of writing the distance from B to the boundary of this box in the bigger box is at least L over 10. The way I usually write it, the same thing, that if I take lambda L over 5 of a B and I intersect it with the bigger box, this is contained in this little box. So what we are guaranteeing is that if I take a point, if I am inside, all I'm really means that the box of size L over 5 is contained in the bigger box. But I could be in the boundary, and if I have a point close to the boundary, I can choose one of those boxes such that if I take the box of size L over 5, the intersection with the bigger box is still inside here. But that's the condition. It's the same thing. This has two more properties. one of them which we're not going to use, but I think I will state it for completeness. And that is that. Okay, so let me. This was number 2. Number 3 is that if I take one of these points, 2 points, A and B, which are center of the covering, but they are different, and then if I intersect them, this is empty. This is used when you do Bernoulli in the continuum, but it's not going to play a role for us. The next one is important. It tells us how many boxes do I have here. Clearly, since I'm covering, it must be at least that much, but turns out it's more or less that. We have this estimate. The number of boxes roughly capital L over little l divided by d. And the other property that is also useful alpha LZD. So these were put in the centers of those boxes, and I'm taking K and N. And if I take any box of this type, 2k alpha plus 1 of A, it's actually given as a union of those boxes, where those boxes are again here x plus alpha LZD, but they are intersected with this box, but not quite this box, but its version in the continuum. So basically I reproduce the covering anywhere I have it. So this turns out to be useful. And let me show now how it's used, and probably the bootstrap multiscale analysis in the end consists of 4 multiscale analysis. Of basically there are 2 types, but they are used in succession. And maybe I will describe in detail how we do the first one to explain some of the ideas. So let me start what will be the first multiscale analysis. So H, so this is a regular Anderson model. And this is where I get this number. And for here, I also need to take this. So this is the alpha corresponding to the measure. And suppose for some L0, I have what is the original hypothesis, that the infamous for every x, the probability of these boxes to be suitable is 1 minus P0, is at least 1 minus this number. Then there is some scale L. Oh, well, I will move things in a minute, such that if L0 is big enough, and I define Lk plus 1 to be y Lk, where y has to be a number bigger than 1,000, and the other condition is that I have the p0 and I need p0 to be smaller than 1 over square root of 2y to the d. If y is 1,000, you get this. Then, I take a number, I'll call it p. P is nothing to do with p0, but that's what I have in my notes. And it satisfies these inequalities, which actually tells you where the condition on theta comes from. I need this number to be strictly positive. So if I get that, we have that for all t, the probability that a box of size Lk centered at x is also theta is suitable is bigger and equal, but instead of 1 minus p0, we get a huge improvement, 1 over Lk to the p. So we got that we only had a lower bound to a lower bound that goes to 1 as k goes to infinity. So we got a huge improvement. And for the proof of the theorem, that's the same thing as simply saying that you proved that the infimum from x in Rd of the probability this is now it's going to be regular, well, but to be regular with a mass depending on the scale. This is just direct translation, but regular, well, is equals to this. Once you have do that, we can now take that and with some k large enough, use that to start the second multiscale analysis, which will basically get rid of the dependence of the mass on the scale. Then we use that to start the third one, and then that fourth one. But let me show you how you get those things from the ingredients already put on the board. So I think I'm going to erase this board. So the proof goes like that. We already have an information from scale little l, and we want to go to scale capital L, which is going to be y little l. So what would I do? I write lambda L and I take the L suitable covering. If all of those boxes were suitable, I could go ahead and prove that the bigger box is suitable just using the consequence of the resolvent identity. The problem is that I cannot assume that all these boxes are suitable, because what is the probability that there exists one of those in the covering that is not theta E suitable? Well, this probability is going to be bounded by the number of such boxes times the probability that one of them not going to be suitable. And let me call this, so let's PL to be the probability that a box of size lambda L is not theta E suitable, or at least a bound. P0 was given, so it's an induction, times PL. Now, this number is much bigger than 1, so this is going to be much bigger than PL. So if I do that, I'm not going to improve the probability. I'm getting them much worse, so this is not going to work. So to do something, I have to be able to improve the probability. I have to need a deterministic situation in which I can use the information I have in scale little l to get what I want in scale big L, but at the same time I have to make sure that my probabilities improve. They do not get worse. The way one does it is to notice that, suppose I take two of those, lambda L and lambda L prime, and they don't intersect, so they are independent. So what can I say? I can say that the probability that both are not suitable, since they are independent, it's going to square. So what I'm going to do is to allow for some bad box. But what I can control, what is the probability that there exists two non-theta E suitable boxes in the covering? Well, if I fix two of those boxes, this probability is PL squared. But how many pairs do I have? Well, roughly this, right? That's an upper bound, but that's not much worse than if you put the binomial. So that's what I got. The difference from what I have before here is that this is 2L over L to the D times PL squared. And this thing here is y, or 2y to the d times PL square. Now, I am going to require PL or P0 to start with, right, to be smaller than 1 over 2y to the d. And if I do that, this is going to be smaller than PL. I'm going to get an improvement. Well, actually, maybe I would want to get a 2D here or something. I can get better, right? So by doing this, because I have a square, that's what's important here, this square, instead of a 1, I can play with PL and y and get something better than what I started with. The price I have paid is that when I look into the complementary set, so the complementary set, I look into the set in which there do not exist pair of disjoint, and disjoint is something you have to deal with too. Disjoint, non-suitable. I am abbreviating a lot. I'm not writing theta, non-suitable boxes in the covering. So what does it mean? It means that I take my box lambda L, I get my covering, I can get here something that is not suitable. This doesn't mean it's the only one. It means that if I take any other box here, this is good, this is suitable, because it's disjoint. But if I take this box here, it's not disjoint. Can be good, can be bad, I don't know. But this, I can take care of it simply because all I really do is that come here and suppose this was a place. This is A, and this, I should make this smaller. This is L. So I enlarge this box and I make it 2 alpha plus 1 L, which meant that I took into account all boxes that intersected. Okay? So I had lambda L of A was my non-suitable box. I constructed something that I'll call lambda tilde, let me just call lambda tilde of A, and in this box I just added to the side. And what is important is that for every point x that is not in lambda tilde of A, when I look at the corresponding box in the covering, there exists a corresponding box such that x is at a distance L over 5, L over 10 from the boundary, this box is good, it is suitable. So my scales are not good, this is little, the other thing is bigger, right? But outside here everything is good. And so I then I think I always have to start from the upper board, from the outside board, so it can go up without covering anything. So now, so how do I do that? So I have the situation of all boxes centered, which contain this point, are good. So I now to the following. So this is the deterministic argument. And the deterministic, first thing, how do I do a good box? If I take X in this box and I know that this thing is suitable, then we already saw if I do that and I took Y, well, I want Y to be far away, so Y is certainly not in this box. That's what I need for the moment. This was bounded by SD, that was the boundary term, but then I got the decay term because this was a suitable box times, well, all this did is to I move to a point I call, let's say, X prime, where X prime I know, I don't know which one it is, but I know where it is. It is in the outside boundary of this box. That's how I deal if a point is in a good box. I can probably, to make more what I mean, this is 1 over theta minus d minus 1, and theta has to be bigger than d minus 1, so I have a small factor here that I would like to propagate. That is fine, and let me change this picture. I suppose this is a bad box, right? And I could start here X, here is Y. I put a box here, I do it, I jump here, I do it, I jump, I jump, I jump, I jump. Every time I get a factor like this, and I just move this point. But at some point, well, if I go all the way close to Y, I don't worry. But at some point, I could come inside my bad box, right? There's no reason why not. I don't really know where I'm going, I just know. Well, so I have to learn how to deal with bad boxes. And to deal with a bad box, I'm going to do the following. So let me just have the picture here. So here is my extended bed box, and here is a Y, and here I took a U which is inside. And I want to estimate, because that's what somehow I got to this term, because it could appear when I keep on doing those things. Well, I am going to do the same thing around this box. So this would be SD. I should write alpha is less than 1, so the size of this is less than 3L. Okay, so just use 3 instead of 2 alpha plus 1. It won't make any difference. 3L d minus 1, and then I should have G of this bad box, let me call it lambda tilde, going from U to the boundary, and then I should have G lambda L E. I go from some V to Y, where V is something in the stereo boundary of the bad box in the big box. I certainly don't have decay for this. That is my problem, right? If I did, I'm in business. Okay, so what do? I assume something with probability I can estimate. That's why I use the Wagner estimate. I assume that, and I'm not even going, I'll make an assumption of the absolute value of the resolvent, the norm. I assume that this is bounded by, could put the 2 alpha 1 plus 1 L to the S, which is the length of the box to the power S. Now, where S is some number, positive number, and I have to figure out which S is going to work. I can't put an arbitrary S. But I know that the Wagner estimates the probability that this does not happen. Okay? That's the key input. So I assume that. So if I assume that, then I do the following. V is outside this box. So this tells me that the box in the covering corresponding to V, where V is away from the boundary, is good. That's how I made the construction. If I go outside the extended bed box, I'm in the good region. Okay? Since I am in the good region, I use it here. So from here, I get that I have SD 3L D minus 1. I will estimate this by 3 from here. This gives me 3L to the power S. And from this, I use that estimate on top. SD 1 over L theta minus D minus 1 times G lambda L E V prime Y. And what I know about V, well, from here I went to something here. Here I did something here. Now V is somewhere here. Let me just say the V prime. The distance from V prime to the bed box is not too big. It's smaller than L. I could be inside, by the way. I could have gone back inside the bed box. So what I do now is simply to say, well, I want to make this term less than 1. So maybe it doesn't give me anything good, but it's not going to screw me up. Okay? So what do I need to do that? Well, this is for large L. I take little l large enough, and I simply have to take theta bigger than S plus D minus 1. Or if you prefer, I should have said, I pick S satisfying this, which I can do because by my hypothesis theta is bigger than this. Okay? Now we are in business. Okay? Now we are in business because let's see what we are going to do. And the way I'm doing bed boxes can be at the boundary. It doesn't make any matter because I'm only take the boundary inside the box, not something that's outside. So I can bounce off boundaries, do it that way, the way I wrote things. So I'll take, so here is my extended bed box. That was the lambda tilde, right? I put X somewhere, I put Y somewhere. Remember that I'm only interested in doing that when they're far apart. I cannot do it, they're not far apart, so I'm not even going to try. So there are basically 2 or 3 cases. For case 1, X is not in the bad box. We then have to deal with the case. X could be in the bad box. I don't really know where the bad box is. Okay, so what do I do then? It's not in the bad box. I put a little box and I jump, right? And I go to a point x1 using that form. And I get that factor S over 1 over L theta minus D minus 1, right? Well, so I jump to here. From here, I jump to here. And I have control of those jumps. They're basically of order L plus 1, L over 10. I jump to here, to here, to here, to here, to here. And then, bad luck, I got here, right? Okay, so suppose I could do that n1 times until I had to stop. So what I'm building is at E x, y. I'll get SD. Now let me write it like d minus 1 minus theta to the power n1. Now I came to this point, right? Well, I use this. And all it says is that I can jump to something here. No gain, no pain. Okay? I do it again. Well, I could have come inside back, right? Doesn't matter. If I keep rolling inside, I can't because I'll go to 0, right? This is lesson 1. So if it goes to 0, I'm happy. I stop. If this is small enough, I stop. If it's not, I'll come out and start moving from some point here, the same way I started from here. If it happens that I come here, this has a contribution lesson 1, I throw it away. But at some point, what I have to worry is that something else goes and I get close to y. Now, I have to stop so I'm not within L of y, because then I cannot use y. L has to be outside. When I do the box to do the jump, L has to be outside the box. So here I did n2 times, right? What happened here? How many loops? 0. Lesson 1. So what did I get? I get another factor n2, and then at some point I got this, some v tilde where I stopped y. Well, I can't continue my procedure with that. I'm too close to y. But this I can estimate by brute force again. And I do the same thing as before. I use what I'm going to estimate by Wagner estimate again. I say the Green's function cannot be too big. I know I can control the probability. I use the same S. I do that. Okay, now what is n1 plus n2? I want a bound from below. How many times can I do it? Well, every time I do that, I jump at most L plus 1. Right? Because I am in a box here. I don't know, it could be here. And I jump to this point here. Well, in the sup norm, I didn't go more than L plus 1. So, really what I should estimate is that n1 over L plus 1, basically, it should be basically the distance from X to the bad box. if I did that, I don't know if I can continue. Maybe I could do more, but if I don't hit that, if I can keep this smaller than that, I have never hit the bad box. I know I could have kept on doing it, right? So I simply say I can make this. I don't get that, but what do? I have to take minus what? Minus L or something like that. Let me just finish this argument. I know the time. Okay, so what is N2? I have a feeling actually that this is actually minus 1 because I'm jumping. Yeah, I cannot do the last one. So because this is not an integer, I take 1. This is a distance from y to lambda tilde minus 1, but I didn't get that close to y, so I have to subtract an L, or 2L if you prefer to make sure. Doesn't matter. So what does it mean here? What it meant here is that what I get here is the distance from a to x tilde plus the distance from y to y tilde. So I basically get x minus y minus 3L, what is the length of that thing, minus another L minus 2. So I should have here minus, I don't know, minus 5L. Put 10L to make sure. I certainly can do that. Okay? And what is this? This is YL to the S. If you want, should I know it's about, should I stop here and start after the break? You would have to tell me what to do.
Maybe we take a break of 5 minutes.
No, because there is a coffee now, isn't it?
Oh, right, sorry.
That I can finish the argument and you can start later, but you tell.
Maybe finish the argument, then if there's a coffee break, we can eat a little bit.
So we can finish it. Okay. Okay. So let's then see. Let's then see what I got here. Okay. What I got here, I want this to be less than equals than L to the theta, which is 1 over y to the theta, L to the theta, right? And so what I want, and this here I can replace by L to 100. It's bigger or equal to L to 100. So what do I need? I need to guarantee that theta plus S has to be smaller than L over 100 times 10L times theta minus d plus 1. If I can do that, I got it. Okay? If I can do that, I got it. Where is the... But remember what L is? That is y times little l. And what do I know about S? S is smaller, so it's enough for me to guarantee, since S is smaller than that, theta plus theta minus d minus 1, right? I have to do that. And what I find out, maybe I want to go through that, and maybe I'm a bit more careful how I get what I have here to get this number. Why did I do that? what I get that theta plus s, okay. No, I'm already on the larger one. Okay. What I find out is that I can do it along this is bigger than equals to the 1000 with the numbers I put here. And if I take y bigger than 1000, I do achieve that. So for large L, I got that, and I got that it's suitable. To finish the proof, and that's actually the harder part, this particular, to finish the proof, I have to show that I have achieved the probabilities I want. So now, this I'll do after the break. What we have shown is that the probability that lambda L is suitable is bigger and equal than the probability, or let's put it that way, because it's easier to do. It's non-suitable is bigger than equal than the probability that there exists two disjoint bad, let me just call them bad boxes, plus the probability that I don't have Wagner in the bigger volume, L to the S, plus the probability that if I take those boxes G tilde A that I constructed is bigger than equals than, if you want, 3 alpha plus 1 L to the power S, but I don't know where the bad box is, so I have to guarantee it by asking that this is true for all possible choices of the bad boxes. And what you have to see is that if you do that, you can get an argument that tells that at some point I get a probability that's bounded by 1 over L to the P, which I'll do in the next after the break.